All right, class, welcome. Hope you guys had a nice break. Mine had some ups and some downs, so that was good. We're continuing with the last little bit of, we're on fluids in general. There's one last thing with liquids, and then we'll cover most of the gases today, because it's just more of the same. It'll go faster because it's all the same concepts. We're just going to deal with air more than water. The last thing we did with liquids, we got pressure. You realize it's a force over an area. It's not just how heavy something is, it's over what it's acting. That should be your tip-off when you see those questions of the depth, how deep something is. It doesn't matter if you're holding back, remember the whole Atlantic Ocean? Or your bathtub. If it's a foot underneath the surface of the water, it's the same pressure. It doesn't matter how much, in quotes, water is above you, just how deep you are, the pressure head. Because you have a lot more water in the Atlantic Ocean, true. But if you're only a foot down, it just matters on what it's pushing on, how much above it. The stuff way over there isn't acting on me over here. And then density, the relationship between mass and volume, how that can change. And so if somebody says 1 kilogram of aluminum, let's make it more obvious. 1 kilogram of styrofoam and 1 kilogram of lead. Physically, you're looking at them. What looks different? The lead would take up less space. It has less volume. If you have a kilogram of each, hopefully that was more conspicuous. You know you're going to need a whole lot of styrofoam to get a kilogram compared to a lead. If you have a liter of water and a liter of molten lead, how will the buoyant force compare to the two if they're both underwater? Good, it's the same. Even tried to trick you because it's water and water. If they take up the same space, volume, they displace the same amount of fluid, water. The weight of that displaced water, Archimedes' principle, the weight of the displaced water is the buoyant force. It's dependent on volume. Very good. So remember density in those things. And then, well, yeah, there we go. So, the buoyant force is one thing. Remember, let's see, so you can connect instead of a new example, the cement blocks, cylinders that we sunk and float. The one that was at the bottom sunk. It was the same volume as the one that floated. If I push the one that's floating underneath the water, hold on to it, and the heavier one sunk on the bottom, which one feels the largest buoyant force? I'm hearing people mumble, just not as confidently. It's the same, because they're the same volume. And so it seems counterintuitive. The heavier one, it's sunk. So a lot of people's intuition is, it must have not as great a buoyant force on it. Because otherwise it would float, right? The buoyant force isn't what determines whether it sinks or floats. It's the net force. It's heavy. And so that buoyant force is not enough. You got buoyant force up, weight down, and if the weight's huge, then it's going to sink. If this one's bigger. If the buoyant force is bigger, then it'll rise up and float. And if they're equal, what's it do? Stays put. It's neutrally buoyant, we'd say, like fish, swimming around, or submarine floating underneath, or a bag of water in a swimming pool. Groovy. Pascal's principle is the last part of chapter 13 on liquids. And I didn't get to any of the board. I don't need much. There. This relates back to the beginning of the chapter, which I just reviewed, the part that's pertinent. Pressure is force over area. Well, Pascal's principle, which is in your book, of course, states a change in pressure at any point in an enclosed fluid at rest is transmitted undiminished to all points in the fluid. Boy, that sounds sciencey, doesn't it? That means if a pressure is exerted somewhere in a fluid that's enclosed, not moving around, so you got a container of water and you push on it over here and it exerts a pressure, that pressure is equally transmitted everywhere in that fluid. So you can push on one side and that pressure will be transmitted onto the other side. And this is my favorite demo for that because I get to make a mess. This is a container. It's got little holes in it. I'm filling it full of water. So the bottom has holes in it. I'm going to push the plunger down, so I'm going to exert a force over an area of pressure. That pressure is going to be equally transmitted throughout the whole fluid, down in all the holes. So when I push on it, can you see the water? It works sideways. Whee! Do it again because it's fun. But you see they're all shooting out at the same. They look symmetric. That tells me they're all feeling the same pressure. They all come out the same velocity. And that is a way to remember and or explain Pascal's principle. Fill it up again. You can even do it vertically. Whee! You get the idea. They come out uniformly. So you exert a pressure in one spot, it's equally transmitted throughout the whole fluid, as long as the fluid's enclosed and at rest. Those are technicalities. But what's that? Yes. Pascal's principle allows us to do hydraulics, and that's what I'm going to do now. Exactly. Yeah.
You said it was evenly distributed.
Evenly distributed.
Is it equal to the pressure that's being applied, or is it?
The pressure will be the same throughout. Pressure. Not necessarily the force. That depends on where it's at, the area over which that fluid acts. Remember, force over an area. But the pressure will be the same. So what we can do with this, if we know the pressure stays the same, pressure, I just did that. I'll just use this one. If the pressure's that on one side, and you can transmit it over to somewhere else, and it's acting over a huge area, because you could spread it out, well, how will the force compare? To keep the pressure the same, to keep that ratio the same, how will the force compare to the one on the right? Bigger, smaller, or the same? Well, heck, let's make it a clicker question then. Get your clickers out. I'll give you some credit. We'll make choices. A, B, C. Bigger, smaller, same. So the question is, how will this force compare to this force? A, B, or C? Polling's open. See what the masses think. Channel 44. Channel 44. While you guys get it out and vote, I'll get the demo to show it. Most of you have voted, it looks like. 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. 60% think it's A, and the others are split. bigger. You win. You are correct. We can look at it one mathematically. Some people like numbers. If this was 10 and this was 10, the ratio is 1. So if we make this area 5 times bigger, let's call it 50. What's the force have to be? Does that help you see it maybe? It would have to be 50 to keep that ratio the same. So you can use that in a hydraulic system. The book draws the pictures better. Let's see. Like this. If you have a big area over here and a little area over here, you can exert a little force on this side. It'll cause a certain pressure in the fluid, but Pascal's principle says that's the same pressure throughout the fluid, so it's the same pressure over here, which means you can get 5 times the force out on the other end. And so you might not be able to lift a whole car yourself, but you could build up a hydraulic system so you can go and make it lift over here if you have it spread it out over a big enough area. A hovercraft demonstrates that. Who'd like to go for a ride? Oh, come on. Nobody, I'll let Brandon. Nobody else wants to go for a ride? Okay, hop on, Brandon. Sit down here. Oh, hopefully the water won't mess it up. But in the middle.
Okay.
Face this thing right in the middle because we got to balance you. This, I guess I should, emphasize here. This has a certain amount of pressure. I do that to emphasize it's not much pressure. I can stop it with my hand. It doesn't lift me. But if we can spread that same pressure on the bottom, which I'll show you when he gets up, over a large area, we can increase the force that it can exert. And so we can raise him up. Let's see, scooch this way a little. This way, sorry. Slide that when you're ready, hold on to it. Grab that and we'll turn you on and we'll see if it works. Go for it. Lifts him up. Boom, change of momentum. All right. You can turn it off. Want to spin? Yeah. Boom! Okay. Thanks, Brandon. So in this case, there's a certain pressure that we're creating. And that fills this up and it comes out the little holes and then covers the bottom, trying to lift this up. So that pressure is created over a large area, which can create a big force, enough to lift his weight anyway and slide him around frictionless.
So if you did it the other way, like put a large force to a large area, you only get a small force out of a small area.
Exactly. He said if you reverse it, you can get a small force out. Yes. Yeah, it works both ways. Usually we use it the way I've been saying for mechanical advantage. It's like a simple machine in a sense. It's just not so simple. And remember, simple machines, levers, pulleys, things, they multiply what? Force, not energy. Energy is always conserved. So this is doing the same amount of work. If you have a hydraulic, take that picture. It's clearer. Let me set this down over here. We can't magically multiply energy, so if we push over here with less force, we're going to have to displace this a bigger distance. What's force times distance? Work. Force times distance. If you just put a force on it and displace it in that direction. So you'll have to use less force, but over a larger distance, because work is going to be conserved, ideally. This force, you'll get a lot of force, but it won't raise it very high. But at least you can raise it. So you can build these so that you can do it. But it works the opposite way too. You can reduce it. If you want to be pushing on this side, so be it. That's Pascal's principle. Here's another way. Let's put this back. Anytime you can use a hot water bottle, that's great. All right, these are lead bricks, if you remember. They're 26 pounds. So there's 54 pounds at least, and the board. And so the idea is we're going to transmit pressure through this fluid. But it's spread over a larger area. So maybe we can get enough force to lift 54 pounds. And how we're going to do that, it's open to the atmosphere. Here's a fluid. If I raise it up, the water runs in. And how does this cause a pressure down here? Gravity, it has weight, the weight of this column. That's like being underwater this far. And let's see, it went to there. It settled that far. So it needs this much water from here down to here, that height. If you could weigh that water, that weight over the little area, you get determines the pressure down there. That's enough pressure to lift these lead bricks. How much pressure did you need? Well, their weight force over the area that I've set up. You see in the hydraulic system here? And we're using the pressure head to determine it. If I lower this, you can see the water rush back in because now this is pushing the water back into here. The pressure, it doesn't have enough pressure head to balance. Yes?
So is the height from the function or from the equation that you showed us the other day, is that the altitude that you lifted it, or is that the length of the hook?
The height that I showed you the other day is the difference between the 2 points in question. So here is the level of the water at this area. So from there to the surface of this.
So it doesn't take into account.
It's not the whole length. See, I can have that down there. Because this weight of water balances this weight of water, so it's like it's not there. So now it settles about here. And so your height difference is this much water. That depth or height, based on the density of water and gravity, that's enough weight of water over that area to create a pressure sufficient to lift this force over that area. All I have to do is raise it up. This is like your IV. My wife was in the hospital yesterday. They had her hooked up to an IV, and I asked for the IV bag afterwards. They gave it to me so I can use a demo. And she was going, "Oh, it's taking forever to drain, sir." Well, just raise it up. Because now it's greater depth, greater height. We're creating a larger pressure difference, and it drains out quicker. Of course, we weren't pushing on it. It was just draining into the sink. But if you want something to drain faster, raise it up. Because this pressure head, due to the fluid, the height of the fluid, adds. Yes? So it's more, yeah, there's pressure in your veins. So it's like the lead bricks trying to push back, yeah. And you got to watch out. If a nurse ever wants to raise this up too high, that increases the pressure. And sometimes it goes in too fast. That can be dangerous. Yeah. And that's another reason the blood pressure, blood pressure cuff. Why do they put it up here? Why do they have you sit? Because they want to measure the pressure at your heart. They're the same level. If you were to measure the pressure, put it on your finger, you know those finger ones or your wrist ones, and you go like this and take your pressure, do you expect the pressure reading to be lower or higher? Lower. And you do it down here, and you can do it. It works. You can get false readings. I mean, they're correct readings, but they're accounting for the blood, the height of the column of blood that's being added on or subtracted off. Higher blood pressure when you stand up in your feet or ears. What do you think? Well, let's see. If we're standing up, here's the pump, here's the source, exerting a pressure. It has to raise the blood up to get up to here. So is basically we're looking at if we could measure the pressure at this point compared to down there. We have the pressure of the heart acting on both. But what else is acting? On what? Gravity's acting on? Yeah, the column of blood. You got a column of blood here. This column is exerting more pressure, but where? At the bottom. So your heart has to work harder to pump things up because it's fighting that weight. And so by the time you're up here, you measure the pressure, it's less because there's less blood above you. Look at your foot. Down here, you got the pressure of your heart pushing, plus the additional height of that column of blood, this column, which weighs something, and it adds more pressure down here on top of the pressure of your heart. So the pressure generally is greater in your feet. Now that you have that behind your belt, start thinking about a giraffe. Oh, perfect example. Yeah, you stand on your head. You guys all know what happens. Blood starts rushing to your head, right? And you can feel that increase in pressure. That's literally why it starts throbbing, because you're having to support that extra column of blood. Both sides. It's open. Pulling's open. The maximum height to which water can be drunk through a straw. I want to see who can reason this out or has read the chapter. I haven't covered it yet, I realize. I want to see what you think. And then we're going to do it. Your clues, since we, won't leave you hanging. What allows you to get water up? Is it your sucking power? Or are you just causing a difference in pressure between the two ends and the air in the room is just pushing it up? Well, if that's true, how much pressure can the air in the room push? And what's it have to hold back? Do you think it's about 10 meters of water? It's that strong? You think our lungs are that strong, or the air in the room, or is it only like 76 centimeters? Or maybe there's no limit? You can just keep sucking away, because maybe you can do it in little sucks and just keep rising up. What do you think? Most of you have voted. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay. 39% thought A, 35% thought C, no limit. That was the majorities. So now we'll do it before I give you the answer. This is water. I put food coloring in it. Would somebody like to come and drink, suck it up? Anybody feel like they got good lung capacity or something? I guess you don't get to see the answer. All right. I watched it if it makes you feel better. So basically, this is open to the air. Just put the straw in the water, and we're going to see how high he can raise it. 76 centimeters, 10 meters, or he can go all the way to the top. Here, come over here. That way you can see your face. That's always fun. And I allow you to suck. Okay. Really? That's it? Come on. There you go. Ooh, ooh. That's pretty good. Go, go, go. That's pretty good. Here. Now, keep doing it. Do that. Seal it off and do a little more, a little at a time. You can maintain the pressure. So what he's doing though in reality, he's lowering the pressure inside him, in his lungs and vocal tract, which decreases the pressure on this side. That means there's greater pressure on that side. Where's that pressure coming from? Whenever you get tired, you can stop. That's good though. Very good. Yeah, okay. Ew. Just kidding. What's pushing the water up? Atmospheric pressure. The air in the room. Air has weight. Granted, you're going to need a lot more air because it's lighter. But what's it balancing? That height of water. The greater the pressure difference, the more weight of water we can support, right? So as he lowers it more and more and more and more, the water level rises because the atmosphere can push it up. Yes?
So would it be easier to drink a milkshake in California than it would be in Denver?
Would it be easier to drink a milkshake in California than Denver? What do you think?
Well, I figure it'd be easier to drink it at sea level because there's more atmosphere pushing down.
And you're right. It would be easier at sea level. The sea level, there's more air above you, so atmospheric pressure is higher than here, where we're 4,000 feet up. That's less air pushing down on us. If we could get rid of all the air on this side so the pressure was zero, then the pressure on this side, the maximum difference we can get to is atmospheric pressure. You see that? If we could lower this side completely, then we'd have atmospheric pressure. Well, how much can atmospheric pressure, what is atmospheric pressure? How much can it hold? Does anybody already know what atmospheric pressure is normally? 1 atmosphere, good. It's
1 atmosphere negligible between 5,000 feet and sea level?
No, it is not negligible between elevations. Atmospheric pressure is 14.7 pounds per square inch. That is not the standard unit. That's just because that's what we relate to as Americans at the moment. It's also 101,000 pascals. Remember, the standard unit for pressure is pascals. That's a force over an area. Newtons per square meter. So it's 101,000 newtons on a square meter. Picture a 220-pound person. That's about a kilonewton, 1,000 newtons. And if you spread that weight over a square meter, that's about what atmospheric pressure exerts. But this is another visual. This is 15 pounds, 14.7 pounds. There's a square inch. So this whole weight on your hand is what you're feeling right now all the time due to the air. We're used to it. So I like imagine quarters, 14.7 pound quarters. Put one on your arm. Come on. Whoa, it's pretty heavy. Take a second 14.7 pound quarter and put it right next to it. Whoa. Now cover your entire body with 15 pound quarters. That's what you're feeling right now. Why don't we implode? Because it's the same pressure inside, balancing. But that's the pressures that's being on us due to the air. Here in Utah, we're higher up. There's less air above us. The atmospheric pressure is typically, it changes with weather too, 12, 13 pounds per square inch. So that is a significant drop. And you climb up to a mountain, yeah, it's even less. We only feel that when there's a difference in pressure. So, another volunteer. Pretty please. All right, over here. I would like you to climb inside. Face the audience, get down on your knees and pull it up around your neck, please. Shop vacs are pretty lame in vacuum cleaners. They might drop the pressure a couple pounds per square inch. So we're going to lower the pressure a little, just a little, inside the bag with you. But we're not going to do it over your head because that's not safe. So your job is just to hold that. I got to seal you up. You feeling okay?
Yeah.
All right. So let's start pulling some air out and lowering the pressure inside and let atmospheric pressure outside do its work. Okay, stand up. Wave. Can you move it
My skin looks gross.
Don't trip. Thanks. What did it feel like?
Like, I don't know, my body couldn't move, like everything was just like, I don't know. Everything was
Did it hurt?
It didn't hurt, it just felt like tight.
Squeezed.
Yeah.
Just felt like it was being squeezed. Well, that was a few pounds per square inch difference from outside to inside. That was atmospheric pressure. You can now feel it. And don't take this wrong, but a few pounds per square inch, but she has a lot of square inches. That's where you're not supposed to. So you spread that pressure over an area. Pressure times area is force. And it's enough force that you're restricted. You can't move. That's atmospheric pressure. Here's another one. And I'm going to need several volunteers for this. Who wants to play tug of war? How about at least 3 on each side? Come on down if you want to play. Three on each side. Let's see. While you're coming down, I'll show you this. These are 2 plates. I just have a little gasket. They just set together. And then I'm going to pump out some of the air, a lot like the shop vac. Oh, good. So this is pulling air out from in between the plates. What's going to hold them together? Pressure due to atmospheric pressure, the air in the room. There's greater pressure in the room now than there is in between. That's all that's holding it together. So, your side. And the first person, get up close, right about here. And your guys' side. First person, get up close. This thing's kind of heavy and I don't want it falling and breaking. All right, now, this is for education. I know you guys are competitive and the floor's a little slippery, so be careful, all right? Go! You guys can't even pull it apart. Now, good tug of war, what's actually doing the force? Not their arms, it's the force of your feet on the floor. You can keep pulling. That's what's actually moving you. I mean, the reaction between you and the floor. But I think the point is proven. Here, you two hold this up high, real close. I'm going to let the air back in so everybody can see. Hold it up nice and high. I'll just open the valve so that the air in the room can come back in and boink, comes apart like that. Thank you guys very much. Thanks. Just suck a little air out, and that's enough to hold up this. And we can figure this out if you wanted to. Let's say we pumped out half of the air. So that's roughly, okay, here, let's say we're 12. So half of that is 6. 6 pounds per square inch difference. Well, how many square inches do we have? Well, you measure the radius, you multiply by pi r squared, remember area of a circle? Pi, round to 3, radius 6, 36, 36 times 3, 100. It's 100 pounds on both sides. So 200 pounds. Well, no wonder you guys couldn't pull it apart. And that's only pumping it down a little bit. So that's to help emphasize atmospheric pressure. Another one. Trying to decide which ones to save for Friday that I won't get to. Let's do this one. Have any of you ever tried to suck an egg into a bottle? It's been around for a long time. Kind of as a trick or in Scouts or something. Well, here's my egg, so I don't have to make it every time. Hard-boiled egg. It doesn't fit. I could shove it in, but it takes work. Point is, it doesn't go in by itself. I'm going to use the air in the room to do the work. If I can create a pressure difference inside, then the lower pressure, higher pressure, the atmosphere will do the work for me and exert a force over this area and push it in for me. But you can see it has to be a significant force to squish that through. And one way to do that is, let's see if I burn myself today. I'm going to heat up the air inside first. And as it cools, as temperature cools, the pressure drops. Piece of cake. Piece of cake. So you can do a lot of work with a difference in pressure, because differences in pressure can create large forces. Now, say that. Oh, the pressure inside dropped. So we heated it up. As things cool, as the flame went out, then the gas inside starts to cool and it condenses, takes up less space, and the pressure drops. That's our chemistry and thermodynamics that I'm not testing you on yet. So the pressure dropped inside, greater pressure outside. So how do you get it out? Uh-oh. I'm going to use pressure. I'm going to blow into it and increase the pressure. Thanks. Didn't see.
So what extent would that work? If you put like a tennis ball on it?
Well, it's got to be flexible. That's why a hard-boiled egg would work. Peel the shell. If it's too rigid, it can't give. And the size matters. If this was a lot bigger but still squishy, it'd need a lot more force, wouldn't it, to shove it in. So you need an even larger pressure difference. And at some point, there's a limit. There's a limit. Now, you got a better feel for atmospheric pressure. We have the value. Another unit. If we convert 101,000 pascals or 101,000 newtons per square meter, or 14.7 pounds on every square inch, these are all units for pressure, what's that work to in water? Pressure is density times gravity times the height of the water. So if we put in the density of water and the gravity on Earth, how high can atmosphere hold up a column of water? Well, I'll spare you. You can work it all out. We can put in 15 pounds per square inch, put in the density of water, put in gravity, and figure out H. And it ends up being 10.3 meters. Just over 30 feet. So, as much as we suck, if we could get this to zero pressure, it's still, the air in the room could only push the water up the tube to 10.3 meters. Just by a difference in pressure. That's as high as we could ever get. Because the atmospheric pressure, the air, the weight of the air on that area can only support a column of water's weight that's 10.3 meters high. How much mercury do you think it can support? More or less? Less, because it's more dense. It's going to weigh more for a less column. And you know how much that is? 760 millimeters of mercury, or 76 centimeters of mercury. Blood pressure is still measured in millimeters of mercury. So when you take your blood pressure and you get 120 over 80, that's millimeters of mercury. Now you have a clue for the amount of pressure that's involved. It would take 760 millimeters of mercury to equal 1 atmosphere. To hold, 1 atmosphere could hold 760 millimeters of mercury. Weather, when they report the pressure, the barometric pressure, same game. Let's do this one. Suction cups. I need that later. This is just a rubber mat. It's not sticky. There's no adhesive. It's flat. You plop it on here, center it. And what it did is squish a little bit of air out from in between the two surfaces. But look, it's a pretty big area. So little pressure over a big area, we can get a big force. There's enough force to support the weight of the stool. And what's holding these two together? Air pressure on top and below, sandwiching them together. Squish the air out. Let the air back in. Pressures equalize and there's no more force, or at least they're balanced. So then, another one. You already did the tug of war, but lest you haven't made the connection yet, suction. That's what a suction cup does. That's what your plunger does in your toilet. When you stick it in, what's it do? It flexes a little, and it squishes a fluid out from in between. When you get your plunger down at the bottom near the porcelain and you squash it. And what's that do? It lowers the pressure between the two surfaces. And the greater pressure is holding it together. So when you pull back up, you're trying to expand and change the pressure difference. And that can force the water or gunk to go where you want it. In this case, you can't pull them apart. You get the idea. Careful. That's a lot of force to do so. And that's a smaller area. If you increase this to a square meter, we could swing from it. We could probably all swing from it. Let's do these. We'll end with that. Friday, we're going to review. I'm going to do Bernoulli's principle. That's where the air starts moving. I got it set up. I'll do it. That way you have a clue. We'll do these last couple demos Friday and review, because our test is next Monday. Bernoulli's principle says it's the last thing we'll do with pressure. We can spread it over areas, and we see how it works in fluids when they're staying put, kind of balanced. If you move a fluid so that it's moving faster, that changes the pressure. That's essentially what Bernoulli's principle says. A fluid that's moving faster has a decrease in pressure associated with it. The faster a fluid flows, there's usually a decrease in pressure associated, and or vice versa. If you decrease the pressure in a fluid, it can move faster. That's the essence of Bernoulli's principle. And this is the clearest way to show it. I'm going to blow air through here, that way. It's open to the atmosphere on that end. There's air in here and water. So you can see that the atmospheric pressure in here is pushing down in here. You got a column of water that's supporting. They're in balance. We're in equilibrium. So the pressures are balanced. When I start moving air across the top of these, Bernoulli says, hey, things change. Pressures adjust. And we're going to see, do you think the pressure increases or decreases here? How about here? How about here? Let's back up. Where do you think the air is going to move faster? Here, here, or here? In the middle. Why do you think the middle?
Because it's the same force going through a smaller area.
Same force through a smaller area. Same force through a smaller area.
So that's going to increase the pressure.
So you think the pressure increases here?
Yes.
Okay.
So that means the water is going to rise more.
If the pressure increases here, that means we're going to have not only atmospheric pressure pushing down, but that increase of pressure. So the pressure is going to be pushing down larger than before, and the water should go down if the pressure increases here. Do you follow that at least? If the pressure decreases here, then there's less pushing down on the water, and the water will rise. Are you with me? Let's see what happens. The pressure rises, so there's less pressure pushing down on the water. So the pressure drops here. Let's discuss that one first. There's something in physics, I don't think the text called it this, but the continuity equation. I'll review tomorrow, or Friday. But it says flow is continuous. The same amount of air that gets through here is going to get through here, is going to get through here. It's continuous. In order for that to happen, when you change shape like this, here, bigger volume, cross-sectional area, you can get air through at a certain rate. It's flowing. If you make it smaller, you got to get the same amount of air through in the same amount of time to keep it aflow. In order to do so, the air must speed up because less air fits in there, so to get it through in the same amount of time, it's got to go faster. You with me? That's the continuity equation. It means big area, little velocity. Little area, big velocity. AV equals, AV has to stay constant. It's a product of area and velocity. So as you get smaller, the air picks up speed. And it's going faster in there, which Bernoulli says drops the pressure. And if there's less pressure there, then there's less pushing on the water and it comes up. This is how old carburetors worked. You'd flow the fluid across the top. It would drop the pressure. And this would rise. And if you go even faster, it'd rise all the way up, get into the airstream, mix, and now you got your air-fuel mix ratio, and it'd go burn and drive your car. That was the point of the older carburetors. Now it's fuel injection. But you can see here the pressure increases because it's pushing down harder. It's kind of like it gets to this point. Stop yelling. And it gets backfed. There's a constriction, and so it gets backed up a little. Increases the pressure here, and you can see that. Moves faster here, drops the pressure, comes up. And over here, doesn't move much. Air's flowing, but not as fast anymore. Because Bernoulli's principle works, believe it or not, on conservation of energy. That's what I'll touch on more Friday. And as you flow through a pipe, there's friction. Have you heard of viscosity? The air is going to rub against itself. That's viscosity. The more it rubs, the less it flows, like syrup. But it also rubs on the inside of the tube, and that slows it down. And so as it goes through, in real life, it loses a little bit of energy due to work done by friction. Turns into heat. And so the air is not moving as fast over here as it was initially. But it is moving faster than right now. And so faster than now means a drop in pressure. And these came up a little bit. Does that make sense?
With the formula, seems like it has a higher force when it's faster. So when its velocity is...
The pressure changes. And when a fluid's moving, the pressure adjusts. Yeah. Not like Pascal's principle where the pressure in a uniform thing stays consistent. And then the force changes. Here the pressure's changing.
Okay, so why does the pressure drop?
The easiest and best way that I want you to remember is because the fluid's moving faster. When a fluid moves faster, there's usually an associated drop in pressure, and vice versa. A fluid is anything that flows, like water, liquid, blood, or a gas, helium, air. If they can flow, it's a fluid. So this applies to air and water. All right.